You have been watching my videos. If you will, please like, share the videos and subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the section Algebra. This question has appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the properties and the concepts of finite groups. This question is from part C. It is a multiple select question. It carries 4.75 marks and the question ID is 704083. The given question is, which of the following statements are true? We are given 4 options. Option 1, that is a statement. Let G1 and G2 be finite groups such that their orders, order of G1 and order of G2 are coprime. Then any homomorphism from G1 to G2 is trivial. We have G1 and G2 are finite groups and their orders are relatively prime. That is, the GCD of these two orders is 1. Then required to prove that any homomorphism from G1 to G2 is a trivial homomorphism. Option 2. Let G be a finite group. Let F from G to G be a group homomorphism such that F fixes more than half of the elements of G. Then F of x is equal to x for all x belongs to G. We have a group G and it is a finite group, and F is a given homomorphism from G to G such that F fixes more than half of the elements of G. That is, F fixes means F of x is equal to x, and it fixes more than half of the elements of G. Then required to prove such a homomorphism is the identity homomorphism. That is, F of x is equal to x for all x belongs to G. Option 3. Let G be a finite group having exactly 3 subgroups. So G is a finite group having exactly 3 subgroups. Then required to find G is of order p square for some prime p. Option 4. Any finite abelian group G has at least d of order of G subgroups, so many subgroups in G, where d of m denotes the number of divisors of m. D of m is sometimes written as tau of m, which denotes the number of divisors of m. And to me, all these 4 statements are looking to be true, because you might have come across these statements in a standard textbook under exercises. So we will see whether they are true or not one by one in the next slide. Let us take the statement given in option 1. Let G1 and G2 be finite groups such that their orders are relatively prime. Then any homomorphism G1 to G2 is trivial. This is to be proved. So we have finite groups G1 and G2. And the GCD of order of G1 and order of G2 is 1. This is same as order of G1 and order of G2 are coprime. Agreed. And any so let us take any homomorphism. Let phi G1 to G2 be any homomorphism, that is an arbitrarily chosen homomorphism. Agreed. And let x be any element of G1. And what is that we want to prove? We want to prove G1 and then any homomorphism is a trivial homomorphism. Let us take an arbitrary element in G1. Now, by Lagrange's theorem, x belongs to G1, therefore order of x divides order of G1. G1 is a finite group by Lagrange's theorem. And the image of x under phi will be phi of x belongs to G2. And again, and G2 is a finite group. Again apply Lagrange's theorem. Then order of phi of x divides order of G2 because phi of x belongs to G2. Agreed. Now, because phi is given to be a homomorphism, order of phi of x always divides order of x when phi is a homomorphism. Right. Order of phi x divides order of x. Order of x divides order of G1. Therefore, order of phi x divides order of G1. Agreed. Agreed. And we also have order of phi of x divides order of G2. And that means order of phi x is a common divisor of order of G1 and order of G2. And therefore, the order of phi of x divides the greatest common divisor of order of G1 and order of G2. That is 1. Therefore, order of phi of x divides 1. Therefore, order of phi x is 1. Agreed. Agreed. So, because order of G1, order of G2 are relatively prime. So, that is the argument. And order of phi of x is 1 means phi of x must be the identity of G2. Right. And phi of x is identity in E2 means any element x is sent to E2. So, since x is an arbitrary, any element, therefore arbitrary element of G1, phi of x1, phi of x is equal to E2 for all x belongs to G1. And how phi is taken? Phi is also arbitrary. Therefore, since phi of G1 to G2 is a trivial homomorphism because phi is an arbitrarily taken homomorphism from G1 to G2. So, phi of x is equal to E2 for all x belongs to G1. That means phi G1 to G2 is a trivial homomorphism because x is an arbitrary element. That means every element of G1 is pushed into E2. Therefore, phi is a trivial homomorphism. How phi is taken? Phi is any homomorphism. Since phi is arbitrary, every homomorphism of G1 to G2 is trivial. So, thus the option 1 is true. Right. We move to the next option. Option 2. Let G be a finite group. Let F G to G be a group homomorphism. It is a given homomorphism which fixes more than half of the elements of G. So, this homomorphism is fixing half of the elements of G. Then you have to prove F fixes every element of G. We are given G is a finite group. Okay. And we have a given homomorphism F G to G. And this fixes more than half of the elements of G. Fixing means f of x is equal to x. Let capital X be the set of all those elements of G which are get fixed by the homomorphism f. That means the set of all x belongs to G such that f of x is equal to x. And what is x? X is a subset of G. Subset of G. And x is non-empty. Why? Because phi of E is equal to E. It fixes E. So x is not empty. And x is a non-empty subset of G. And trivially X is a subgroup of G. Since F fixes more than half of the elements of G, what will be the order of X? Order of X will be order of G by 2 because F fixes more than half of the elements of G. Right. And it is easy to see that X is a subgroup of G. And we have already seen X is a non-empty subset of G. And we want to prove X is a subgroup of G. What is G? G is a finite group. When G is a finite group, X is a subgroup if we verify closure law in X. That is sufficient. That means X belongs to X, Y belongs to X will imply XY belongs to X. That is sufficient. Then X will be a subgroup of G because G is a finite group. Right. XY belongs to capital X. That means F fixes X and F fixes Y. Now, F of the product XY is equal to F of X into F of Y because F is a homomorphism. F of X is X, F of Y is Y. This is equal to XY. That means F fixes XY. That means XY belongs to capital X. For all XY belongs to X. Because G is a finite group, that is sufficient for us, and capital X will be a subgroup of G. Agreed. So we got this one. X is a subgroup of G. When X is a subgroup of G, we apply Lagrange's theorem. Then the order of X divides order of G. Therefore, order of G is equal to some k times order of X for some positive integer k. Right. But order of X is greater than order of G by 2. Therefore, order of G is greater than k times order of G by 2. Suppose you take k is equal to 2, then order of G is greater than order of G. This is not possible. And when k is equal to 3, order of G is greater than 3 by 2 times of order of G, which is untenable, which is not possible. And for any k greater than or equal to 2, this is not possible. Therefore, k is equal to 1 is the only solution, and order of G is greater than order of G by 2 is okay, will work. K is equal to 1 means order of G is equal to order of X. Thus, order of G is equal to order of X. G is a group, X is a subgroup, and equal groups. Now, order of G is equal to order of X will imply X is equal to G. That means that X is equal to G means F fixes every element of G. That is, F of X is equal to X for all X belongs to G. Thus, we got whatever is required in option 2. Thus, option 2 is also true. Right. We move to the option 3. Option 3. Let G be a finite group having exactly 3 subgroups. Then G is of order p square for some prime number p. So we have a finite group G. Further, G has exactly 3 subgroups. Let us say the identity element alone, the whole group G, and a proper subgroup H. So these are the 3 subgroups. Right. Note that order of G greater than order of 3. Why? Because the groups of order 1 and 2 do not have 3 subgroups. They only have trivial subgroups. Right. So order of G is greater than 3. So now case 1, we deal with 3 cases. Case 1, let order of G is equal to P, where P is a prime number. That means order of G is G is a group of prime order. Recall, every group of prime order has only 2 subgroups. They are trivial subgroups. That is the subgroup containing the identity element alone and the whole group G. So therefore, and G should have exactly 3 subgroups. Therefore, order of G is not equal to P. Agreed. then possibility 2, case 2. Suppose that order of G is at least 2 distinct prime divisors. Order of G has at least 2 distinct prime divisors, say P1 and P2. That means P1 divides order of G, P2 divides order of G. Now recall Solo's first theorem. Therefore, G has subgroups, say H1, H2 of orders P1 and P2 respectively. Now, the trivial subgroups are already there. The group containing the identity element alone, the whole group G. Now we got two subgroups, H1 and H2. So how many subgroups? It will have at least 4 subgroups, that is subgroup containing identity element alone, H1, H2 and G. Therefore, order of G does not have 2 distinct prime divisors. And you can also extend this argument. This argument covers the case when order of G is P1 to the power of K1 into P2 to the power of K2 into etc. Pm to the power of Km, where m greater than or equal to 2, P1, P2, Pm are distinct primes. It also works in that case. So therefore, what is the option left to us? The option left to us is order of G could be a prime power. So option 3, suppose that order of G is equal to P power R, where R greater than 1, where P is a prime number. Then by Solo's first theorem, G has subgroups of order P, P square, P to the power of R minus 1, besides our trivial subgroups, the subgroup containing identity element alone, the whole group G. So thus, how many subgroups we have? These will give you R minus 1 subgroups, and these are 2, R minus 1 plus 2, R plus 1 subgroups are there. Thus G has R plus 1 subgroups. But G should have only exactly 3 subgroups. This is possible since G has exactly 3 subgroups. R plus 1 is equal to 3. That will imply R is equal to 2. Therefore, order of G is equal to P square. Thus, we get the assertion that G is of order P square for some prime number P. Yeah. Thus, the option 3 is also true. Right. We move on to the fourth option. Option 4. Any finite abelian group G has at least D of order of G subgroups in G, where D of M denotes the number of divisors of M. This D of M sometimes is written as tau of M. Tau of M. Tau of M denotes the number of divisors of M. Agreed. Here you have to note down that it is a finite abelian group. Finite abelian group. There is a clue in that. Right. We have G, any finite abelian group. Order of G is equal to n. Let us say. Now we recall the converse of Lagrange's theorem, that it says the converse of Lagrange's theorem holds for finite abelian groups. For finite abelian groups, the converse of Lagrange's theorem holds. That means for each divisor D of n, there is a subgroup of order D of G. Let D be a divisor of n, then G has a subgroup of order D. So thus for each divisor D of n, there is a subgroup of G of order D. Now how many divisors are there for n? D of n. So this shows G has at least D of n subgroups, where D of n is the number of divisors of M. What is n? Order of G. So that is G has at least D of order of G subgroups. Yeah, that's what we wanted in option 4. So thus the option 4 is true. So summarizing all the options are true. The answer to this question is option 1, 2, 3 and 4. That is the detailed discussion of the solution of the given problem from algebra, which talks about the results or properties of finite groups. As I have already told you in the beginning of the discussion, that these options do appear in standard textbooks under exercises, and that is many students do remember who are preparing for this kind of an examination, that is national eligibility test. For them it is a cakewalk. They remember this and they say all of them are true. If you do not know, then it will be difficult in the examination, that you have to convince that these results are true. It will take a long time. With these few words, we have come to the end of the discussion. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.